So, acids and bases, fundamental concepts, part 3, definitions. Today we're going to get into the trickier, different ways to define acids and specifically the different ways to define bases. Now, those of you, if you remember from the first video, we talked about and we pretty much explained what it meant to be for a solution to be acidic or basic. Just quick little recap here. An acidic solution is a solution that has more H plus ions than OH minus ions, and a basic solution is one that has more OH minus ions than H plus ions. So that's pretty simple and straightforward. So it seemed pretty simple and straightforward that an acid is something that when I add it to solution, or if I add it to water, it's going to increase the amount of H plus and it's going to decrease the amount of OH minus. Likewise, a base is something that when I add it to water, it's going to increase the amount of OH minus and it's going to decrease the amount of H plus. Pretty simple, and that is basically true. That is what an acid is. That is what a base is. But there are different ways of accomplishing that goal, those different goals, and because there are different ways of accomplishing those goals, that's where our different definitions come in. And the two main definitions you need to be aware of for inorganic chemistry are the Arrenhius definition and the Bronsted-Lowry definition. Now, both of these guys define acids pretty much the same way. These are just some definitions that you're going to want to memorize. But the Arrenhius definition of an acid is something that donates H plus ions. Okay? Let me write that a little bit neater there. Donates H plus ions. And that's also the definition of a Bronsted-Lowry acid as well. Bronsted-Lowry acid is something that donates H plus ions. Sometimes they'll reword this, instead of saying H plus ions, they'll say donates protons, but because that's basically what an H plus ion is. Where they differ, the Arrenhius definition and the Bronsted-Lowry definition, is the way that they define bases. Okay, an Arrenhius base is something that donates OH minus ions. Okay, but a Bronsted-Lowry base it does not make any mention of the OH minus ion at all. A Bronsted-Lowry base is one that accepts H plus ions. So notice this, the Bronsted-Lowry definition of an acid and the Arrenhius definition of acid are basically the exact same thing, but where they differ are their definitions of base. Now let's move on. So now that we've seen these definitions, let's kind of work on them in practice, okay? And we're going to start with the Arrenhius definitions because that's the easiest one. Those are the easiest ones, and honestly, it's the most intuitive. It's the simplest definition. And if you were to try to come up with your own definition of what an acid is, very simply and straightforward, this would probably be the definition that you come up with. So we start here with our neutral solution here, okay? The neutral solution, which is, neutral water, pH of 7. It has a whole lot of H2O molecules in there, but also some H plus ions and some OH minus ions. We covered that in the first video. And since the amount of H plus ions and the amount of OH minus ions are the same, it's neutral. If I want to make this acidic, I need to make sure that there are more H plus ions than OH minus ions. So Arrenhius says, let's say if I want to make this acidic, that's easy. Way to make it acidic is easy. I need to put in a lot of H plus ions. Okay, if I put in more H plus ions here, that's going to make it acidic. A good example would be something like HCl. If I put HCl in solution, it's going to dissolve. It's going to give me some H plus ions and some Cl minus ions. The Cl minus ions are irrelevant. This H plus ions is what I'm going to do. I put this in there. It's going to increase my H plus ions, so it's going to be an acid. So that's pretty simple. An acid is something that donates H plus ions. Okay, and that's just very simple, very straightforward. And likewise, the definition of a base is very straightforward too. Let's erase this, let's erase this extra one, let's erase this. So we go back to a neutral solution. Let's say we want to make this a base, okay? We want to make it a base. Okay, well, a base is something that has more OH than H plus. So if I want to make this a base, Well, Arrenhius says that's super easy. I just have to add some OH minus in there, okay? And the easiest way to do that would be something like adding sodium hydroxide, NaOH. If I add NaOH to water, it's going to dissolve. It's going to give me Na plus ions and OH minus ions. The Na plus ions are irrelevant. These are the ones that matter. I'm going to be dumping more OH minus ions in there, so that's obviously going to increase the concentration of OH minus ions, so that's going to be a base. So a base is something that donates OH minus ions. Very simple, very straightforward. I mean, if I want more H plus ions, what do? I donate H plus ions. If I want more OH minus ions, I donate OH minus ions. And that's pretty simple, very straightforward. Well, why isn't that definition sufficient? And the problem with this definition is that there are some substances, most notably NH3 ammonia. Now, you can look at this, and this clearly you can see, does not have any OH minus ions. There are no OH ions, okay? There's no oxygen in it, so there's no OH ions in there. So, by definition, this cannot be an Arrhenius base, because it doesn't have any OH ions to donate. Nevertheless, when we put this in water, when we put NH3 in water, we see that the OH ion concentration increases. If we put NH3 in water, the pH lowers, the pOH rises, and it becomes a base. The solution becomes basic. So NH3 has to be a base, but it doesn't fit this definition. So we need to expand our definition somehow. And that's where Bronsted-Lowry comes in. Now, as we said before, the Bronsted-Lowry definition of an acid is the exact same, donates H plus ions. Okay, all right, no different. Ben, back to the example, HCl. I put that in water. It's going to donate H plus ions, Cl minus ions. Cl minus ions are irrelevant. I'm going to have more H plus in here, so it's an acid. Bronsted-Lowry views acids the exact same way as Arrhenius does. But what we expand upon here is the base. Bronsted-Lowry says a base is a proton or a H plus acceptor. Okay, let me write that a little bit neater. It accepts H plus. Because Bronsted-Lowry sees that remember what I'm trying to do here is I'm trying to increase the proportion of OH minus to H plus. And Bronsted-Lowry sees there's another way for me to do that other than me just plugging in H plus. What I can do is let me pull out some H's. And specifically, let me do this. Let me look at these water molecules there, because remember, this is what it is. Remember, acid-base chemistry is really the chemistry of water. There's a lot of water here present. Look at this H plus over here, this H on this water here. What happens if I pull that out and add it to this and turn this into NH4? What's going to be left behind? Well, if that HOH, if I pull off this, look what's left behind. What's left behind is the OH minus. You see that? If I pull this hydrogen off of that water, I am left with an OH minus. So if I pull enough hydrogens off, that is an alternative way for me to increase the amount of OH minus. You see how they do that? Okay, so this is the other definition, and this definition accounts for ammonia. It explains why ammonia is a base. So this definition is a little bit broader, and it's a little bit better. A couple of other advantages of the Bronsted-Lowry definition. Okay, the Bronsted-Lowry definition accounts for why some things such as water can be either an acid or a base. Okay, this is a very important thing when you study buffered solutions. But look at H2O. Okay, H2O can accept a hydrogen ion and it can turn into H3O, hydronium, or H2O can split. It can donate an H plus ion and turn into a hydroxide ion. So this Bronsted-Lowry definition showing the relationship between Bronsted-Lowry and water, it shows the relationship with water, and it also shows how some things like water can be either an acid or a base.